Welcome to the Are You GCSE Physics Ready playlist. This playlist is packed with example questions and guided solutions for every GCSE Physics topic. So it's the perfect tool to help you test your understanding. If you feel like you might need a quick review of this topic before having a go at the questions, or you would just like the ideal revision companion for these videos, then do make sure to download my free GCSE Physics revision notes, linked in the description below. If you're ready, let's dive in. Okay, so let's calculate some moments. So first here on the left-hand side, we have calculate the moment, and we have a distance of 2 millimeters and a mass of 3 kilograms. So first things first, what is a moment? Well, a moment is a force multiplied by a distance, but in particular that distance is the perpendicular distance between the pivot and the force. So in this instance here, what is our force first? Well, that's been provided by the weight of our 3 kilogram mass, and we know our formula for weight, or we should know from our previous work, that it is mass times g. So we have 3 times g is 10, gives me a force of 30 newtons for this first picture. So the moment is that force times the distance, and my distance is currently in millimeters, so I need to divide it by 1,000 to get it into meters, so that's 2 times 10 to the minus 3. Then I can multiply them together. 30 times 2 times 10 to the minus 3 is 0.6, and then my units are Newton meters, because you are multiplying a force newtons times a distance in meters. Okay, next one, calculate the distance. So this time we've been given the moment, which is being caused by this 50 kilonewton force. So again, my moment is equal to the force times the distance. Therefore, in order to find the distance, I need to take the moment and divide through by the force. So my moment is 10, dividing through by my force. Now it's 50,000 there because my force is in kilonewtons. So I need to make sure that that force is in newtons first. So that's 50 times 1,000, or 50,000. And then if I do that, 10 divided by 50,000, I get 2 times 10 to the minus 3 meters. Okay, so first on the left here, I've been given 3 different moments. All those crosses are the pivots, and all the arrows show the forces. So the point here is to work out what distance am I actually looking at to plug into my equation force times distance, okay, because it's not always that straight line distance that they give you between the pivot and the force. So for example, in the first one here, you can see that my force is not at 90 degrees to that line that they've drawn in there. If it were at 90 degrees, it would follow that dotted green line down there, and it doesn't. So the first thing that I know is that that distance that they've given me, that black line, is not the distance that I need to use, but instead I need to find the distance that is perpendicular to that force. So I need to draw a line from my pivot, which is my cross there, to my force arrow, which is perpendicular to that arrow. So if I draw that line in there, perpendicular to that force arrow, that will give me the distance d that I need to use to find the moment of that particular force. Let's do another couple of examples. So example 2, I've drawn this on a slant. So the pivot is there, and the line that I have given to my force is that line there. Now, in this instance, actually, that force is already perpendicular to that line that I've given. So that is the distance that we're going to use, that line drawn in there. And what about in 3 here? Well, let's see. Is my force perpendicular to the line? No, because if it were perpendicular, it would go along that green line that I've just drawn in there. Okay, so now let's try and find instead a line which is perpendicular to my force and goes to my pivot. So that would be that line there, perpendicular to my force, and I can join it straight to my pivot. So that there is the distance that I would be using for my equation. Okay, next part here, you've got a question where you've got a force and distance like that. So the force is not perpendicular to the distance that is given here. So if I wanted to try and find the moment, I wouldn't be able to multiply those two things together. I would have to multiply the force by my distance d dash there, which is perpendicular to my force. But that's not what my question is asking here. My question is asking, how can I maximize the moment? And to give me two ways. Well, the first thing that you can do is you can increase that distance that you're using, d. Even though that's not the distance that I'm multiplying with, by increasing that distance, I would be increasing the distance that I would use in my equation anyway. So always increasing the distance between the pivot and the force. The other thing I can do here is if I actually put that force perpendicular to that distance, that will increase the overall moment by doing that. And I could also just increase the size of that force as well, which would also increase my moment. Okay, we've got a complicated diagram here. That triangle is a pivot, and then we have forces either side of the pivot. So on the right hand side we have that 15 Newton force, and on the left hand side we have the 20 Newton force, and we have the 10 upwards force, and these are all at various distances from my pivot. The 15 and the 20 are both 3 meters away from the pivot, and the question is, how far away is the 10 Newton force from the pivot so that this bar would be horizontal or in equilibrium? So we are going to use our principle of moments, and that is for this bar to be horizontal in equilibrium, the clockwise moments need to equal the anti-clockwise moments. Let's go back to the picture and just decide quickly which of these moments are acting clockwise and which are acting anti-clockwise. So my 20 Newton one there is trying to pull this bar down in an anti-clockwise motion. My 10 Newton one, because it's trying to pull the bar up, so even though it's on the left hand side, it's actually trying to produce a clockwise turn. And my 15 Newton one pulling down on the right hand side is also trying to produce a clockwise turn. So I have two clockwise and one anti-clockwise moment. So let me start with my anti-clockwise moment there from the 20 Newtons. So I need to find it by doing force times distance. So that is 20 times distance from its pivot, 3 is 60 Newton meters. Now I can look at my clockwise moments, and I'm going to look at the 15 Newton one first. So that is force times distance, 15 times 3 is 45 Newton meters. Then I'm going to consider the moment coming from that 10 Newton force there. So force times distance is 10 times the distance. I don't know the distance of the 10 Newton force to the pivot yet. That's what I'm trying to find out. So how do I find that out? Well, I go back to my principle of moments and I set all of my clockwise equal to my anti-clockwise moments. So that is 45 plus 10 times d, those are my two clockwise moments added together, equals 60. If I move that 45 over to my right hand side, I get 15 equals 10d, and therefore the distance of this 10 Newton force should be 1.5 meters. Okay, next we have a similar scenario. I've already drawn in clockwise and anti-clockwise stuff for you, and we've got all the distances there. I am trying to find what is the mass of the object on the end there so that this bar is in equilibrium. So again, I'm going to be using my principle of moments. Clockwise moments equals anti-clockwise moments. And my first step is to therefore find all of those individual moments. So let's start with the anti-clockwise moments. So that is just from my 3 kilonewton force there. So it's a force times a distance. And the distance in total, you can see from the bottom there, that 3 kilonewtons is 5 plus 10 centimeters away from the pivot. So it's 15 centimeters. But I need these in newtons and in meters to help me out here. So 3,000 newtons times 0.15 meters gives me a moment of 450 Newton meters. Now, I wouldn't have had to bother converting with these kinds of questions had all of the forces been in kilonewtons and all of the distances in centimeters. That would then eventually have given me a force that was in kilonewtons. But I think for completeness here, if I convert them all, especially because that 900 is not in kilonewtons, it will make it really clear what I'm doing. I'm finding anti-clockwise moments and equaling them to clockwise moments. So next, my clockwise moments, I have the first one, which I'm going to consider, which is the one coming from the 900 newtons. So 900 times 0.05, to get that 5 centimeters into meters, is 45 Newton meters. And then my other clockwise moment is going to be the force that I don't know yet, times 0.15, 15 centimeters in meters, gives me 0.15 F. Then I need to set my anti-clockwise equal to my clockwise, so 450 equals 45 plus 0.15. Moving that 45 over, we have 405 equals 0.15 F. Dividing through by 0.15, we have 2,700 equals F, force. But it didn't ask me for the force. It asked me for the mass of the object. So mass is weight divided by g, and of course this force is the object's weight. So 2,700 divided by 10 is 270 kilograms, the mass of that object. Okay, now for some gears questions. So one gear interlocks with another, first has 5 teeth, turn clockwise at 3 meters per second, state the direction and speed of the second gear with 20 teeth. Okay, so firstly, let's talk about the direction. That's the easiest bit. When you have interlocking gears, if you turn one way, it will turn the other one the other way. If that were locked with another one, it would turn the one the other way, and so on and so forth. So they keep swapping the direction that they're turning. So if the first one is turned clockwise, the second one will be turned anti-clockwise. Okay, now for the speeds. So the key thing about the speeds is to do with the ratio of the number of teeth for your gears. So let's write those out first. 5 teeth versus 20 teeth. And I want to try and simplify this ratio down as far as I can. So here, both of these numbers, 5 and 20, have a common factor, and that is 5. So I can divide both sides of this ratio by 5, and it tells me that the teeth are in a ratio of 1 to 4. So that is saying for the small gear with 5 teeth, for every one of those teeth, there are 4 teeth on the 20 tooth gear. Okay, now what does this ratio tell me, this 1 to 4? Well, what it tells me is the small gear, i.e. my 5 teeth one, is having to move 4 times as fast as the 20 teeth one. So I've got 1 to 4. It's the same ratio for their speeds, but the other way round. It's your 5 tooth one which is moving 4 times as fast. So then I can write a little expression, because I know that my 5 tooth one is being turned at 3 meters per second. So 3 must equal 4 times the speed of my 20 tooth one, because that 5 tooth one is travelling 4 times as fast as my 20 tooth one. So my 20 tooth one is going at a speed of 3 over 4 meters per second. Okay, and you can see if you times 3 over 4 by 4, that gives you 3. And so those 3 to 3 over 4 are in the same ratio as 1 to 4. Okay, a crane has a counterweight to balance the weight of the object it is trying to lift. Explain, spelt wrong. What must happen to the size of the counterweight if the object gets moved further to the end of the crane? So, forgetting this question being absolutely littered with grammatical errors, let's see what it was trying to ask. So we have my beautiful artistic picture of a crane, and it has a counterweight on the left hand side, and it has the object it's trying to lift on the right hand side. Okay, and those are about the pivot, the long piece of crane that goes vertically upwards. So what was the question again? It was saying that if you move the object further and further towards the end of that right hand side of my crane, what must happen to the counterweight so that this crane remains horizontal? So the further the object goes, obviously the larger the distance is of the object from the pivot. So you get a larger moment because your moment is your force times your distance, which means you've now got a larger, well, in this instance, in this picture, clockwise moment coming from my object. So I need to match that with a larger anti-clockwise moment coming from my counterweight. And basically that means that my counterweight needs to be larger. I need to have more of it, more mass, and therefore more force to provide the same large moment that my object is now providing. Of course, you could also just move your counterweight further and further from the pivot as well, which would have the same effect. It would create a larger anti-clockwise moment to match that larger clockwise moment.
Just before we go into the tips and tricks section, if you do want some extra advice to getting that grade 9 for your GCSE, then why not download my free 20-minute exam success guide? Just click on the link in the description below. I'm going to give away all of my best advice and secrets, and completely for free, so why not?
Okay, tips and tricks for this section. Force, not mass, times distance. Yes. So your moments are a force times a distance. And if you are just calculating a moment, then you will usually leave that in Newton meters, and therefore will have to convert any masses that you're given in the question into a force by multiplying by G. And you'll have to convert distances in centimeters or millimeters to meters, and forces in kilonewtons or millinewtons or whatever it is into newtons before you multiply them together. There is a catch to this, which is if all of your forces are given as just masses, you can actually get away with just using the masses in your calculations. And if all your distances were given in all centimeters, you can get away with just using centimeters instead of meters for your calculations. If there's ever a mixture of the units, you can't do that. You must convert them all into newtons and meters first. But you can get away with it if they're all the same wrong unit. However, do be aware, if you do that, and let's say you're trying to find the final distance, you will then get that distance in centimeters or whatever the unit is that you have been using. So you need to be really consistent with the units. My advice would probably be to convert everything into newtons and everything into meters and to work from there. But it could be quicker if every distance were in centimeters to just leave all the distances in centimeters and pop out the final distance in centimeters at the end. So just be aware of that. Okay, perpendicular distance, yes. They might give you a diagram. It might have a few different distances on it. Make sure that you found the perpendicular one before plugging it into your equation for your moments. 3 ways you can increase or decrease your moment. Change the distance from the pivot, increase or decrease it depending on whether you want to increase or decrease the moment. Make your force perpendicular if it wasn't already perpendicular, and increase the size of the force. So apply any or a mixture of those 3 fixes to any question that asks you increasing or decreasing moments. Finally, don't forget that this sum of clockwise equals sum of anti-clockwise moments is called the principle of moments, which they can ask you to state. And that's what you need to write. You need to write the sum of the clockwise moments equals the sum of the anti-clockwise moments for the system in equilibrium, okay, or when it's horizontal.